out by looking at a very easy, simple scenario. And this is a scenario where the chemical and the electrical forces are acting in the same direction. Okay, not like the scenario we just talked about. So if you have an electrical driving force based upon degree of separation of charge that wants to move particles into the cell, and then you also have a concentration gradient that wants to move those particles into the cell as well. Okay, the electrochemical force, which is the sum of both of those forces, will naturally act in the direction of each of those forces, which is the same. And the magnitude of that, or the strength of that force, will be the sum of the electrical and the chemical forces. Does everyone understand that? Very easy, very simple. A very good example of this was the electron transport chain. So in the mitochondrial matrix, we had a negative charge, whereas in the inner membrane space, we had a positive charge. And then we also had a concentration gradient. We had more protons in the inner membrane space, and we had almost no protons in the mitochondrial matrix. And so we had both a chemical driving force and an electrical driving force that favored those hydrogen ions moving into the mitochondrial matrix. Okay, so it's nice and easy and simple when both of those forces are in the same direction. Let's talk about what happens when the chemical and electrical forces are in opposite directions. Okay, so when this happens, the sum, or the electrochemical force, is going to act in the direction of the stronger force. So that's where we are going to have to decipher which of the forces is stronger, which of them is most dominant. Okay, and when we do that, the magnitude will be the larger force minus the smaller force. Yeah, I'll say that again. So if the chemical and the electrical forces aren't acting in the same direction, if they're opposing each other, such as that first scenario we saw with potassium, then the stronger force will dictate, or the stronger force will influence the direction of the electrochemical force. Okay. And then the magnitude will be the larger force minus the smaller force. Now I want you to look at this question and think about it for a little bit, and then we'll talk about it. So if a chemical gradient existed, under which conditions would a particle not be transported across a membrane, even if it is permeable to that particle? Okay, so let's see. What are some thoughts about this question? What are we thinking? If a chemical gradient existed, under which condition would a particle not be transported, even if the membrane is permeable to that particle? Okay, if the electrical driving force was larger, if it were stronger, we would have movement in the opposite direction, wouldn't we? What would have to happen for there to be no movement? It would have to be what? Equal. Thank you. They'd have to be equal. Right? They'd have to be equal. So when the electrical driving force is equal but opposite to the chemical driving force, there is no net movement. Right? There's no net movement. Even though we have a chemical gradient, even though the membrane is permeable to that particle. When the electrical driving force and the chemical driving force are equal and opposite, there is no net movement. Okay? That brings us to talk about the equilibrium potential. Right? The equilibrium potential. What is the equilibrium potential? This is a type of membrane potential, and this basically exists when the electrical force is equal to the chemical force and the forces are acting in opposite directions. Okay, I'll say that again. The equilibrium potential is the membrane potential that exists when the electrical force is equal to the chemical force. They're the same amount, same magnitude, but they are acting in opposite directions. Hence, there is no movement of the particle in question. Okay, does everyone understand that? It's going to be very important for what we're going to talk about going forward. So the equilibrium potential is usually standard for a specific ion. So for example, in this scenario, the equilibrium potential of potassium is negative 94 millivolts. But then the membrane potential is also negative 94 millivolts. And because of this, they will cancel out. There will be no net movement. The equilibrium potential is really indicating to us what the chemical driving force looks like. Whereas the membrane potential is indicating to us what the electrical driving force looks like. What does that separation of charge look like? And when these two forces are equal and opposite, there is no net movement. Okay, very important. Now, the way we indicate the equilibrium potential is E subscript X. Okay, so don't get too anxious about seeing that. That X just means that we're talking about some ion in question. So the X is basically a placeholder, right? And in this scenario, that X is basically potassium. So the equilibrium potential of potassium is what we're speaking about specifically. But if you see EX, it's whatever ion in question that we're talking about. And just to reiterate that, if the membrane potential, which is indicated as Vm here, is equal to the equilibrium potential of the ion in question, whatever that ion is, then the force is equal to 0. Everyone understand that? Any questions on that bit so far? Any questions? What questions do we have? Okay, let's keep going. So let's really look at how we decipher or how we determine which of these forces is the dominant force. Which of these forces is going to dictate the direction of the movement? Okay, so how do we determine the electrochemical driving force if we have two different forces? Now, the first thing we want to identify is the chemical driving force and the electrical driving force direction. Okay, so that's sort of the first thing we want to decipher. What is the direction of the electrical driving force? What is the direction of the chemical driving force? And then there are 4 scenarios that we can come upon. The first scenario is that they are in the same direction. Okay, they are in the same direction. And if the electrical driving force and the chemical driving force are in the same direction, then the electrochemical driving force, right, the sum of both of those forces, will also be in that direction, right, will act in that same direction. That's sort of our first scenario. That was the easy, sort of convenient scenario that we looked at with the electron transport chain. The second scenario would be if the electrical driving force and the chemical driving force are acting in opposite directions. Okay? If they're acting in opposite directions. And what we have to do at this point is basically, I'll write this in red here, compare the equilibrium potential and the membrane potential. Okay, we're going to compare the equilibrium potential with the membrane potential. We said that the equilibrium potential is an indicator of the chemical driving force, right, of the solutes, of the concentration gradient. So I'll write here that the equilibrium potential is indicative of a stronger chemical driving force. And we also said that the membrane potential is indicative of the electrical driving force. It's indicative of that separation of charge, right? The degree of separation of charge. So if we compare the equilibrium potential and the membrane potential, we can figure out which of the two forces is the dominant force. Okay? So let's see here. The first scenario is that the equilibrium potential is greater than the membrane potential. So I'll say if the equilibrium potential is greater than the membrane potential, then what happens? Given what we just talked about. If the equilibrium potential is greater than the membrane potential, then which of these driving forces is dominant? Come on, the chemical driving force, good. So if the equilibrium potential is greater than the membrane potential, then the chemical driving force is also greater or more influential than the electrical driving force. Okay, can everyone see that? All right, actually, let's put here, hence the electrochemical driving force follows the chemical driving force. Okay. Let's look at a second scenario. What about if the equilibrium potential is equal to the membrane potential? Then what? We talked about this a little bit earlier. What about if the equilibrium potential is equal to the membrane potential? Then what? No net movement. No net movement. Perfect. No net movement. All right, then the CDF is equal to this EDF. The chemical and electrical driving forces are equal, and then the electrochemical driving force is equal to 0, and the ions are at equilibrium. Hence, no net movement. Okay. Okay. And then our fourth scenario here is if the membrane potential is greater than the equilibrium potential, then the opposite of that first scenario is true. We said that the membrane potential is indicative of the degree of separation of charge. This is the electrical driving force. Okay, and so if the membrane potential is bigger than the equilibrium potential, then basically the electrical driving force is the dominant force. It's going to be greater than the chemical driving force. And then the electrochemical driving force will follow the direction of the electrical driving force. Okay. Okay, does that make sense to anyone? Any questions on this? Any questions? So basically, we're determining the direction of the electrochemical driving force. And because it's made up of two different forces, because it's made up of the chemical driving force and the electrical driving force, we need to take both of these forces into account. right? If they're acting in the same direction, that's nice and easy and simple, and the sum total, the electrochemical driving force, will be in that direction, okay? If they're in opposite directions, we're gonna compare the equilibrium potential and the membrane potential to determine which of those forces is the dominant force, which of those forces will influence the direction. Okay, and we said if the equilibrium potential is greater than the membrane potential, then that means the chemical driving force is dominant. And so the electrochemical driving force follows the direction of the chemical driving force. We said if they were equal, that the net movement was 0 and that there was no movement of those ions because they were in equilibrium. And finally, if the membrane potential was greater than the equilibrium potential, then the electrical driving force was the dominant force, and so the electrochemical driving force will follow the direction of the electrical driving force. Okay? Yes, Ryan?
You said there was 4 scenarios. It seemed like 5.
1, 2, 3, 4. So if they're in the same direction, then if they're in the opposite direction, it can either be that they are the equilibrium is greater than the membrane potential, they're equal, or the membrane is greater than the equilibrium potential. Does that make sense? So there are 4 scenarios here. Does that make sense for you?
Okay. Yeah.
Right, so this sort of is the general heading for these 3, basically. Okay. Alrighty, let's get back on track. Any questions on that? That's going to be very important. Okay, so just to summarize here, we said that the equilibrium potential could either be stronger than the membrane potential, or it could be weaker than the membrane potential. And we would look to those numbers to decipher whether or not the net movement would be in the direction of the chemical driving force or the electrical driving force. So let's look at this first scenario in this image B. Okay, so we have a chemical driving force that is built on a concentration gradient where potassium wants to leave the cell and move outside the cell. We also have an electrical driving force, right, that is built upon the separation of charge here, where potassium wants to move into this negative environment because it's positively charged. And so what we do is we look at the equilibrium potential. Again, for potassium, it's going to be a fixed number. So don't get too bogged down with memorizing any of these numbers. If you are to calculate, or if you are to make a decision on any of these in an exam, for example, you will be given the membrane potential, you will be given the equilibrium potential for that ion. Okay? And so, as we can see, the equilibrium potential here is stronger than the membrane potential, and so the direction of the chemical driving force wins, or is more dominant. Okay, and if we subtract the electrical driving force from the chemical driving force, we'll get the magnitude of the electrochemical driving force, and we know that it will be in the direction of the chemical driving force simply because the equilibrium potential is greater. Okay, let's look at an opposite scenario here. So in this side, the membrane potential now is stronger than the equilibrium potential. And what did we say that meant? Which of those 2 forces was dominant? The electrical driving force. Perfect. So because the membrane potential is stronger than the equilibrium potential, the electrical driving force is the dominant force here, and so the electrochemical driving force will follow the direction of the electrical driving force. And again, the magnitude will simply be the electrical driving force minus the chemical driving force. But the net movement here will be into the cell simply because we're honoring, or the dominant force is going to be the electrical driving force.